Okay, as promised, these are the solutions to the final review. I solved them on paper and I'm going to kind of just scroll through them here. Number one, the distance was 900 kilometers. You just add the two distances together. The displacement, you had to use Pythagorean theorem, so it was 671 kilometers. The angle for the velocity and the displacement is 63.4 degrees. Average speed is total distance divided by 8.5 hours was the total time. So the average speed is 106 kilometers per hour, whereas the average velocity was only 79. So there's number one. Number two, if the boat's traveling 10 and the stream is traveling 5, you have to use Pythagorean theorem to find the overall, which gives you 11.2 miles per hour, and it's traveling at an angle of 26.6 degrees. I guess you could just say downriver or south of east, depending on how you did your drawing. The number of meters that light travels in a year, you start with the speed of light, 3e to the 8th, multiply it by 60 seconds in a minute, 60 minutes per hour, 24 hours per day, times 365 days in 1 year, and you end up with 9.46 e to the 15th meters. Number 4 was a motion diagram problem. So you basically just have to count and do some simple math. So the first one, the average speed from A to E is 4 meters per second. Position at 3 seconds, that's the, basically this first dot is 0, so 1, 2, 3 seconds is right there. So its position is 9 meters. The displacement of the change of position from C to E is 12 meters. And the overall acceleration, you just look at how the speed is changing, and it goes from 1 meter per second here to 3 here to 5 here to 7 here. The pattern is that it's getting bigger by 2 each time, so the acceleration is 2 meters per second squared. Number 5, these are the givens right here. Number 1 here shows you the equation of motion that you start with, and then I showed you the steps to get the acceleration a by itself, which brings you to the equation there, number 3. And when you plug in your numbers, you get 3.11 meters per second squared negative. I'm going to try to speed up a little bit here because otherwise this video is going to take forever. Next page, number 6. It's a very similar problem. I'll just kind of show you the steps there. You can pause here if you want, but the answer is 36 meters per second squared. That should be 36 meters per second because you were looking for the initial velocity. Number 7. Again, it's an equation of motion problem. There's the steps. Pause here if you like, but the answer should be 4.41 meters per second squared. Number 8, you start with the force diagram. So it's in constant motion, which means that both the up and down forces and the side-to-side forces are going to be equal and opposite to each other. So I did the sum of the force equation for the x direction and the y direction, and the amount of force that you need to keep this thing moving at a constant speed turns out to be 161 newtons, that number on the far right there. Okay, moving right along. Number 9 is a similar problem with a dog sled, but now it's not moving at a constant speed, so your net force in the x direction is no longer equal to 0, it's equal to ma. I'll leave it there. You can kind of pause and look at these numbers and see how I did it. But the coefficient of friction is 0.36 for your answer. Number 10, if you're pulling a bucket and it's accelerating upward, that means that the tension is greater than gravity. So there's your equation, and your answer ends up being 46.4 newtons. Number 11, so you got two forces. You got to break both of them in their x and y directions, so I made kind of a little T-chart there. You end up with a total x force of 52 newtons. The force that I labeled as number 2 here is actually negative in the y direction, which is why you see a minus 31, so the total y force is negative 16 newtons. The overall force is 54 newtons at an angle of 17 degrees. And that angle would actually be south of east. Okay. Number 12, same type of problem. I made a little T-chart. We'll zoom in on that. So these are your equations from the drawing. There's the drawing. And there's my solution. So T1 is about 255 newtons, T2 is 441 newtons, and T3 is about 509 newtons. Now in the back of your book, if you check the answers, They round it a little bit differently, but the answers are basically the same. Okay, number 13. You've got a modified Atwood machine here. It's a block and a pulley going over a ramp. So there's your force diagram on the block on the tabletop. There's your force diagram on the block hanging off the edge. Notice gravity is bigger than tension here, whereas over here tension's bigger than the force of friction, which is why it's moving to the right. So here's your equations, and because the force of friction is bigger than the force of gravity produced by the smaller block, the situation will remain in equilibrium. If the force of gravity by the smaller block were to overcome the force of friction, then the system would accelerate. And because of the numbers that I calculated, because it's in equilibrium, the tension in the rope is equal to the weight of the smaller block, because tension is a responsive force, so it ends up being 117.6 newtons. Okay, this projectile motion problem I'm going to go over quickly because we've done this before. It's just like on the midterm, different numbers. So your answer is 83 meters from the base of the cliff. Right, number 15. So there's the initial information. That's how you find the initial velocity in the y direction. 35 sine of 35 is 20, and you need that here to find your height. So there's the equation of motion and how I solved it, and the answer ends up being 20.4 meters for the maximum height. The next part, you just use the range equation and plug in your numbers. It's real simple, and your answer is 117.5 meters. Feel free to pause anywhere along here as you want to see more about what I did. Okay, number 16. So here's the roller coaster problem. 1, 2, and 3 there. They show you your answers. So your velocity is 15.7 meters per second. Your centripetal acceleration is 16.4 meters per second squared. Your centripetal force is 49,348 newtons. Here's the force diagram. So when you're at the top, the normal force is much smaller. In fact, in some cases it would actually go down to almost zero because you basically feel weightless, because you are no longer slamming yourself into the seat as much. All the forces are directed towards the center of the circle. So because the centripetal force has to stay the same, the normal force actually has to get smaller. Whereas down at the bottom where you feel heavy, the normal force has to get bigger than the force of gravity in order to maintain that same centripetal force. So you feel lightest on the top and you feel heaviest on the bottom. And again, there's your previous 3 answers. Oh, there's a typo here, by the way. The period is supposed to be 6 seconds, not 60 seconds. So if your numbers aren't matching mine, I apologize. That is the reason. Number 17. On planet X, your period of rotation is just 2 hours. Apparent weight is what you get when you take the normal way of calculating the force of gravity, which is just mg, and then you subtract off the centripetal acceleration, because centripetal acceleration actually causes you to feel slightly lighter. So the faster the planet is spinning, the lighter you would feel. The idea being, if the planet was spinning fast enough, your body's own inertia would be enough to carry you off the planet and you just take off into space. So on Earth, you would just be looking at the force of gravity, but when you're moving faster like this, you have to calculate the centripetal acceleration. I showed you both here. So here's the centripetal acceleration on Earth, and I showed you how you would calculate it. If you plug these numbers in, you get a very, very, very tiny centripetal acceleration. So technically, your apparent weight, the heaviness that you feel right now, is a little bit lighter than what you would calculate as your force of gravity, because you have a small centripetal acceleration to include in that number. But because the period for planet X is so much smaller, your period in seconds is 7,200. When you put that number into the equation, you get centripetal acceleration of 4.85, which, when you subtract it off of gravity, actually makes quite a big difference here. So you would feel almost half your weight on planet X because you're spinning so fast. In other words, you'd feel a lot lighter. Okay, 18. This is a Kepler's law problem. I'm just going to leave it there. It's pretty simple. Start with Kepler's law. TA is for the period of the asteroid, TE is for the period of the Earth. You end up with 140.3 Earth years. This picture right here, now this problem may seem difficult, but it's actually just a really simple conservation of energy problem. The idea is the total potential here is equal to the sum of the potential that's left here and the kinetic here. So that's what this equation right here is showing you. If you plug in the numbers here, the masses will actually cancel out. That's why this equation has no m's in it. And you get a total height of 1.3 meters. That's up here at the top. The force diagram for this point right here on the right side of the loop, there's only the centripetal force, which in this case is the normal, and the downward force of gravity. To calculate the normal force, because it's the only force acting in the centripetal direction, you set it equal to mv squared over r. And so the normal force is the centripetal force, and its value is 3.2 newtons. Okay, if you want to find how high it goes, you use this equation of motion that we've been using so much, solve for h, and this is what you end up with. Now the only thing to consider here is that its maximum height, its final velocity is 0.